Well, in 1960, we returned from Okinawa. My dad was Air Force, and he was stationed at Patrick Air Force Base, which, as you know, is just down the road from Cape Canaveral. So I went to high school there. I was a freshman there and saw the launch of Shepard, Glenn, and I loved math and science. Said, that's what I want to do. And since Dad was Air Force and he'd been an Air Force pilot, I always loved airplanes and all that stuff. I said, okay, this sounds great. So going into high school, and then I got interviewed by the Dean of Engineering at Florida State University, and they was looking for co-op students, specifically for NASA. So I said, okay. Went to Florida State in the engineering school in astronautical engineering. Wound up coming to Marshall as a co-op student in '65. And it was amazing. I mean, to come here, and so much was going on, and everybody was so busy, and we were just all heads down trying to get ready. And it didn't matter that I was a co-op. It didn't matter that I was 19 years old. So I got into a lot of good work really quickly and got to do some things that really kind of showed me what engineering was. I'm not sure people that go into engineering school really know what it is, and I think here it's special anyway, but that really hands-on experience was wonderful. And going back to school, it was kind of multi-motivational, both directions. Really loved it. I reported to Marshall, signed in. The next day, they sent me out to school. I'd just come back from school, but they sent me out to IBM, and I had to learn to program a computer, because as you know, it was early in the computer age. So they sent me off post to IBM, and what I had to learn was machine language, because that's what we coded in. So everything was machine language commands. There was none of this BASIC and Fortran and all that stuff. Didn't even exist. And we only had, I think somebody told me one time, about 275K of memory on the whole bird. So the whole trick was to be able to put as much process into as few steps as you can get, because you really had to compress the memory. So that was the challenge for programmers. Fortunately, I wasn't a programmer, but I could understand it well enough to do my real job, which was punching data into data cards, physical paper cards that we generated a stack about this long and fed them manually through a printer. What all those cards were data from the flight tests of the Saturn and the engines, because what we were trying to do was make sure the trajectory was refined. You had to know the weight and where the center of gravity was constantly to know how much fuel you were burning, what the burn rate was at a particular time, the angle, the acceleration. Everything had to be understood. So I did that for an entire co-op term, was work in, and it was called weight and mass control for the Saturn. The next term I co-opted, I was very fortunate in being sent to the materials division, which was part of Propulsion Vehicle Engineering Laboratory at the time. And there I got into some really great stuff. One of the things they were doing when I got there was trying to figure out, I don't know if you know what tribology means, but it's kind of lubrication surface physics. So I was in this group, and what they were trying to figure out was how do they lubricate the clamps that were holding down the Saturn V on the launch pad to make sure they all released in the same microsecond. So it's not goose grease, it wasn't bacon grease, it wasn't anything that was currently available. They were developing things that were called molybdenum disulfide lubricants and graphite mixed with that. So I was the co-op, so I get to do a lot of the testing, and it was a lot of long nights and a lot of long days, but I loved it. I'm working on a real problem contributing directly to this vehicle that everybody was so excited about. And I think it was just thinking about that as I sat there those long hours, and one of the things I would think about was who would have thought to worry about that? I was so impressed as a young person with the detail and the questioning and the curiosity and the the delving to know all the answers about everything, no matter how small. And this being such a small thing, but you had a really bad day if they didn't all release at the same time. And of course, it all worked. So what I found was if you asked questions, people were so happy to help you. And when I went to materials lab, it was the technicians. I wanted to learn how to operate the equipment in the laboratory. I wanted to learn why they did what they did. I wanted to learn what the data meant and how you accumulated the data and how you analyzed the data. All those things to part of answering a big question took that delving down into that solution level. But everybody wanted to help. They wanted to help you learn. They wanted to help you do well in this very strange environment of working. It was not school. So it was, there was never any question about finding help. And that was that way throughout my entire career. I remember when I became a chief engineer, and the first problem I got handed was a big discussion between dynamics and stress in a structure. I called Bob Ryan. Bob, help me. I don't understand enough about this. I'm not a mechanical engineer. I'm not a dynamics specialist. So he gave me his version. Jim Blair gave me the lecture on dynamics. I said, okay, we're all going to get in a room. And I had them explain the problem to me, by which they came up with their own solution. So it was all about their getting people talking. But it was never a question of people being willing to teach you, because they all loved what they did. They loved what they knew. They were the ones also that started a little program here at Marshall's, very low-key, called Concept Verification Testing. And I was fortunate enough to be engaged with that, and Dr. Mary Helen Johnson and Doris Chandler and Whitaker was involved with us, and we became a female crew to CVT. And the idea there was being able to, we as scientists, being able to interact in this modular environment on the ground, but to help us understand, how do you integrate? How do you make the science operate? How do you schedule crew? How do you train them? How do you communicate when they're a process of doing experiments? Is it they're alone doing their thing? Are you connected to the ground? It was harder than I thought it would be, because I thought it would be like walking into my lab and doing my thing with my hardware. Well, no, my hardware was up there. It was not there. And you couldn't just run to the toolbox if it wasn't on board. That was part of the problem, is figuring out, what do you take with you? Because if it wasn't there, you didn't have it. So it was, I think when they were learning to integrate the racks, it was an interesting little thing. They were trying a track approach where we'd roll the experiment racks in on the tracks. Well, I went in there one day, we were doing the checkout and testing, getting ready to run our mission, and I reached up and touched a rack, and a spark about this long flew. The electrical had been wired up wrong. So we found out very quickly, okay, test and checkout. We need to do more test and checkout. So that became a real effort, especially for Space Lab and everything, and a lot of that work, of course, was done at KSC, and teams from Marshall would go down there, because you began to understand that if you're not as careful with this as you were with the launch vehicle, then there's going to be an issue. There are going to be things that don't work, and it all needs to work. It's a big effort to put these things together. But I think that was quite an eye-opener for me. I said, wait a minute, it doesn't mean just because somebody built it, it was built right. So it was a big learning point to say, okay, ask again. So it was a lot of learning in not just operating in space. Johnson Space Center is very good at that with their astronaut corps. They do a fantastic job. But then being able to take this science and observations of science and the data of science, and how do you make that work? How do you get the most out of it? So we got out of CVT, how do you configure a rack? How do you load an experiment? How should you build them? And it was quite a learning experience. And then Marshall got the assignment to actually develop Space Lab, and Jack Lee was a big project manager of that. And that turned out, of course, to be just a wonderful program that led directly to accomplishing the science on Space Station. I mean, we knew that we were kind of a thing. I mean, an all-female crew, and I guess everybody thought we'd get in fights, but of course we never did. But you know, it's when two needs merge And I think there was a need at the time for something that reinforced the job that Marshall and NASA was doing, and that looked more to the future. And I think with everything that was going on in the country, it was probably a good thing too. I mean, it wasn't until 1975 they opened up the astronaut selection to women, and Mary Helen and I both applied to that in '75. So it was. It met our needs. I think it was a learning experience for all of us, and it was intellectually, mechanically stimulating to do it. So we never felt badly about it. I mean, it was all goodness. If it served them, great. And we were here working for the team at Marshall, and we got a lot of learning out of it that helped us much more in Space Lab and later. That was a shock. I mean, we were invited to go over and use the neutral buoyancy simulator, but at the time we were also starting to really design and develop experiments for space, but we didn't understand zero gravity, how it felt, how it affected the design of your machinery. Marshall was already training astronauts, certainly in the neutral buoyancy simulator, and the opportunity to go over there and learn and work with hardware changed how we thought about our hardware. It wasn't like our lab. And we needed that understanding very early on to be able to not only do things for ourselves, but advise those scientists from the outside that we were working with as to how to do those things. Seeing myself in the scuba suit was nothing I ever really enjoyed. But it was, I think it really contributed to the job. It contributed to our understanding of what the people doing this stuff in space really had to work with. And it's hard. It's really hard. And we didn't appreciate that. So much of it was about just the human factors aspect of operating in space. And I mean, an astronaut knows that once they've been into space. They know it when they've been through the neutral buoyancy training and zero gravity flight and stuff like that. But we didn't have anything like that here. But using the neutral buoyancy simulator, that made human factors real. It wasn't reading a textbook. It was actually things that mattered a great deal. Doris worked in the systems laboratory, which I had hardly heard of at the time because I was still in the materials lab. And she was probably the best systems engineer I'd run into at that point in my career. So she helped all of us, as the rest of the crew, understand how to get things together and what we observed and what needed to be communicated. I think that was a big thing too. When we would try to do something on board and we would, well, it was a struggle or we were trying to do something different, she said, you need to tell them, because it's the engineers who are learning how we're going to go about doing this job. And it was all about communicating that, not just doing our thing, but just as we were a team in other things, how do you become that team between science, operators, and engineers to really learn those lessons and get that data out there? And I'd say Doris was really instrumental in that. She was a leader of that team. I didn't feel like it was ever an issue. I was the only woman in the engineering school, so maybe that helped. I was acclimated. But coming here, actually in the materials division, I wound up working with Ann Whitaker, who was already here. And Ann was tremendous as a mentor and all of that. But it was never really an issue. I think it was the time, and we were all pressing for 69. So we really had to get all of us doing the job, pulling the wagon in the same direction at the same time. And it just was never a problem. I had so many mentors. I had mentors I didn't even know I had. I mean, when you're 17 and 18 years old, you don't know what that means. And you're taking book learning, and trying to translate it into this work environment. But I think back on all the people that helped me, people like Ann, people like Bob Schwinghammer, Bob Ryan. There were so many that contributed so much. Again, at the early, it was the technicians that taught me really hands-on stuff. They said if you didn't get your hands dirty, you weren't doing the job, and I agree with that. It's there was mentorship that was not formal. I don't think we had a mentorship program here for many, many years after that. But somehow the informal worked, and I think it was part of the team structure, the team attitude. When you're working with other people and you can see they need help, you helped them. And that was mentoring at the best level, I think. Very one-on-one, very personal. It could be technical, it could be personal, it could be anything. But it was always there. I think it was very much a team culture, and I think that's what made it work. Marshall was a very strong team. Everybody shared their knowledge, as I already talked about. I remember it's a little further down than obviously the landing on the moon, but when we launched Skylab and the shield came off, I was in materials laboratory then as an engineer. Talk about problem solving. Bob Schwinghammer was the head of the lab, and I have never met anybody that had more problem-solving capability, wrap his arms around any problem, and give you an excellent and practical solution. So the laboratory immediately, everybody coalesced. Bob gave the marching orders. We all went off to develop a solar shield to save Skylab. We had worked on Skylab so long. Funny thing about that was before it was launched, someone realized there was no American flag painted on the side of the vehicle. So our job then in the lab was to come up with a flag that could be painted, which means you had to have paint that would survive that environment. The real problem with the paint was we had spent years testing materials to make sure they didn't crud up the optics because we were flying the Apollo telescope mount on Skylab. So we had kept those optics clean for so long, and now we had to paint a red, white, and blue flag on the outside that was going to be exposed to all these optics. Oh, my goodness. Well, it was typical Bob Schwinghammer. He came in one day with cans of paint, set them down. He said, "These work on my boat, and it's resistant to UV. We're going to see if it'll work on a Skylab flag." And by God, it did. The flag got painted on plates. We put it in, we baked it, we outgassed it long enough that it wasn't going to contaminate the optics, and there we go, problem solved. But it was just amazing how that man could think. I mean, who would think of boat paint? Come on. Put it. I think it's one of the things that developed in people at Marshall. I know it developed me as a systems engineer, because when you face a problem, there is a core to the problem. But then beyond that, all the disciplines wind up getting involved in finding the solution and implementing it. So you had people in manufacturing, you had people in development, you had people in research, you had people in the process to get this thing approved for flight. So it took all of that together in a very integrated system approach to make it all work. Well, you were immersed in it. You were part of the system automatically when you came in, and everyone had value. Everyone was contributing. Everybody had something they were good at or knew more about than somebody else. So it all got thrown in the pot, and the stew was amazing. Well, there weren't a lot of boundaries between organizations. You went and did your job. Now, I'm sure at upper levels, maybe all that was going on. But, boy, if we needed to go work with somebody from systems or thermal or structures, it was all for one and one for all. It just didn't matter to us. It was who could help and who was willing to get involved. I think the one that was really caused a real click in my head was I was able to go down to the Cape and watch Apollo 8 launch. And that was such an experience and it was emotional, and it was moving, and it was the nation in leadership, and it was just so much of, oh, this is what I've been doing for these years, and this is what I want to do forever. So it was just being able to be there, see that happen, hearing everything that went on when those guys orbited the moon was just amazing. I mean, our planet was no longer alone. The moon was connected to us, and we were connected to it. And then I was also able to go down and see Apollo 11. But I think Apollo 8 was the one that grabbed me the most. I said, I'm a NASA engineer. This is what I'm going to do. I think it was dynamic, but it was also frustrating because we'd get engaged in a program and then it would dissipate. And while the formulation and the job to work with Congress and work with headquarters to really develop the shuttle, which of course had been on von Braun's plate from day one, was a time of real uncertainty. There were rifts and layoffs here at the center. I was fortunate enough to be sponsored by NASA to go to graduate school in that same period of time, so that kind of kept me on a little better keel. But we were also at the same time doing some really great stuff. The Apollo application program started, it was not about Apollo just going to the moon. It was about science in space. And putting men into space is one thing. Expanding the realm of science and exploration with people is something that really hadn't been done in space. So it was an opportunity. I started working on some material science experiments, trying to understand how zero gravity affected the way materials solidified. Are there better materials out there? Started looking at the behavior of fluids, the behavior of animals, plants, all these things that we did not know. And of course that all culminated really in Skylab, which was a great scientific laboratory. We did astronomy, we did material science, we did bioscience. It was just amazing. And being able to be engaged in that at the scientist level, although I wasn't a scientist, I loved it. And so it was a matter of taking that and the engineering and putting those together, and then working with scientists who had proposed to fly to help them understand what it took to get an experiment from an idea to the hardware to approval for flight, through the flight operations, and then being able to bring them back the data they needed to test their theories. So I think it was really the beginning of a larger science program. So some things were winding down, but other things were increasing. So by the time we were ready to do shuttle, we were thinking about Space Lab. We were thinking about how do you make the shuttle a vehicle that's really going to be able to accomplish science in space. Because you can do automated science, a lot of observatories do that, but having the people interaction with the experiment is something that if that's missed, their observation and their knowledge and what you are gleaning out of it is so helpful to the scientist who is still on the ground to understand what happens. So I was involved in Skylab and then Space Lab, and then Space Station. So that thread of science and exploration just is carrying through today. I think the legacy of Apollo is at many different levels. I think one, the legacy of that leadership and that shining star that the United States put out there. That leadership was maintained through these other programs. We have an International Space Station, which the U.S. primarily leads. I think it's been at the human level. It's connected people to space like they never had been connected before. And at a micro level, my 7-year-old granddaughter came up to me the other day and she says, "Grandma, did you know the universe is expanding?" Really? To me, I was so amazed that a 7-year-old would know that. When I was a 7-year-old, you didn't know space existed, didn't understand what it was or what it could be. So the generation of today, not my children, but my grandchildren, take that for granted. They understand space is an expansion of Earth. They understand there's a big universe out there. They understand there are big dreams and big things that can be done, which I wouldn't trade anything for. To have been able to be involved in that and engaged in that put that thought in my granddaughter's mind was priceless. Wouldn't do without it. I think the STEM programs that are going on in the schools now are a great step in the right direction because I think they feed a child's curiosity. And whether that kid is a boy or a girl, I don't know that it really matters. We need people that can think. We need people to be creative. We need people to be able to expand their thoughts and be able to problem solve, understand how to do that. My granddaughter's actually in a STEM class. So they come up with an idea and they build things. They actually build things. So I think that helps. It's not enough. I think there are enough impediments out there still in society that creates a problem, just images of boys versus images of girls. I don't know if that's ever going to change, but I know it's a lot better than it used to be. Several years ago, there was like 30% of the engineering class at some universities were female engineers, and I think that's amazing. But it needs work. It needs work. I've got one daughter who's an engineer. I've got another one who's a financial person, and I've got a son who's a journalist. So, me raising them didn't matter. But it has to be what the kids are interested in, and that interest has to be piqued early, very early in their lives. And if you catch them when they're 5, 6, and 7 years old, they're going to do something with it because it's going to intrigue them and excite them to do something different.